Hello, freshmen. We're just going to pick it up from where we were before. This is part 2 on electromagnetic rays. We had stopped the video before, but now we're just going to pick it up. So here we are in the electromagnetic spectrum, the EM spectrum, and we have the diagram of different forms of light. So here we're looking at the electromagnetic spectrum. Notice that we are in the radio end, and the frequency of this light is 10,000 hertz, which seems like a lot. That's 10,000 waves per second. But in terms of light, that's not a very high frequency. It's actually low frequency. As we go from low frequency and the frequency starts to increase, now we go from radio into microwave. Notice there's an overlap between radio and microwave. Why? Because it's the spectrum. There's no way to tell really where one part ends and the next begins. But right around 10 to the 8th, which is 100 million waves per second, we're now in the microwave end. And as we keep going, and as the frequency increases, now we go 10 to the 10th, and we go 10 to the 12th. Now we're in infrared, 10 to the 12th, 1 trillion, that's a 1 with 12 zeros after it, waves per second. As we keep increasing our frequency, now we're in the visible light part. Now check this out. Infrared goes from here to here, from 10 to the 12th, 10 to the 14th. Visible light is this tiny chunk. And in the visible light part of the spectrum, we get all the colors of the rainbow. So it goes from red, orange, yellow, green, blue, indigo, and violet. And again, it's hard to tell where one color ends and the next begins. That's why it's a spectrum. But notice, it's not a lot of the whole spectrum. It's this little piece. As we go past that, then we get into ultraviolet. This is the end where insects will use ultraviolet to see. Again, snakes will often use infrared. We use visible light. Anyway, so here we are in the ultraviolet end. We're at 10 to the 16th. We keep increasing our frequency. Now we're in X-rays. And again, take a look. This is confusing. Gamma rays and X-rays? Sorry, I don't make the rules. That's the way it goes. As we increase our frequency, now we're at 1018, 10 to the 20th. That's a 1 with 20 zeros after it. Mm-hmm. And as the end, we keep increasing our frequency, and now we're at the other end of the electromagnetic spectrum at 10 to the 24th, which is a trillion waves per second. So obviously, that's a lot of waves per second. Also, as we pan down, take a look at what happens to the wavelengths. So here we are in radio. Check this out. Approximate wavelength in meters. It's 10,000. It's 10,000 meters long for radio waves.
From one crest to the next crest.
That's 10 kilometers. So now maybe you're figuring out why we use radio waves to broadcast radio over long distances, because the wave will go that far, okay, in between each signal. So we're at 10,000 meters, and then as we decrease wavelengths, now we're going from radio into microwave. So let's keep going. We're going to keep decreasing our wavelength. That's 1 meter, down to a centimeter, down to a tenth of a millimeter, and now we're into micrometers. And look what's happening here. As the frequency is increasing from the top one, our wavelengths are decreasing. Now we're on the end here, that we're in visible light. We're getting smaller. 10 to the negative 10th. That's a tenth of a billionth of a meter. Now we're in the area where this wavelength is smaller than the gaps between the molecules in your skin, and now we're in X-rays. As we get smaller and smaller, now we're at the point where small enough to be in, think of it like Ant-Man, right? We're getting small enough that we can fit in between the molecules inside your cells, and now we have light that can get into your cells, your skin cells, your body cells, and that's why gamma rays can be so destructive, because they can make their way inside those tiny little spaces. Like Ant-Man could get in between the molecules inside the missile in the first Ant-Man movie, for you Marvel freaks. Anyway, so bottom line, let's pan out. As we go from radio to gamma, the frequency is increasing. As we go from radio to gamma, the wavelength is decreasing. So let's take a look. We have that kind of down here. We have it as we go from low frequency, as we go across, we go to high frequency. But low frequency also means long wavelength. So long wavelength as the goes down to short wave, And it would follow that, look, if you're at the ocean and you got hit with one wave, and then you waited a lot, and you got hit with another wave, you probably wouldn't care too much. But if the waves had a higher frequency, it was like wave, 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 that probably would knock you over at some point. Each wave is delivering a certain amount of energy. So here, let's think about it. If low frequency, we're going to have a low energy wave. Okay, and let's go across. So as the frequency increases, now we're at a high energy wave. So gamma rays not only can get in between the atoms, but they're also very destructive because they're also high energy. So let's get down here.
Billions of them hitting you every second.
Right. Again, this end of the spectrum, not dangerous to humans. As you go across.
Through visible
light, now we're at dangerous to humans. So let's keep in mind here.
Visible light is kind of the barrier
Yeah.
between what's not dangerous to humans
and what is.
And what is dangerous to humans.
Right, so all the people that say, like, there was a big thing like, people's cell phones near their heads are going to cause brain cancer because all of that EM radiation is going to be right next to your skull. That's kind of impossible, all right? That is kind of impossible. It simply won't happen, so that's, sorry, fake news. It's like, infrasonic radiation from wind turbines. Not going to hurt you because sound doesn't have radiation, but whatever. I like facts. And then, so that's not dangerous. Visible light is also not dangerous. Obviously, going to pan down a little bit that way. No. Yeah,
sorry.
That's okay. And then...
That's the dangerous side.
All right. So now, last bit. These are all light. And all light travels at the speed of light. And that's just a fact. It doesn't matter if it's radio, visible, microwave, gamma rays, X-rays, infrared. It doesn't matter. They all travel at the same speed. Moving over. And that speed is, because it's constant, we give it a special name. So when speed is usually we use V, but instead of V, we're going to use C. Why are we going to use C? It's a long story. All you need to know is the speed of light is denoted by C.
It's from the Latin word for light.
Yeah.
Yeah.
So, and that speed is 3 times 10 to the 8th meters per second, which we covered yesterday. In a vacuum, if there's nothing in the way. Granted, light going through air doesn't go a lot slower than that, but it does go slower. But the fastest speed is that in a vacuum, which again is 186,000 meters per second. Okay, so that is some characteristics of the electromagnetic spectrum. That was a long video. Hey, we broke it up into 2 parts for you. Accidentally, but still. I hope you liked it. If you have any questions, please let us know. Again, it's a lot of, you might have been, if you're curious about this stuff, you might have been watching it and going, well, what? And again, light's real hard to understand. Not that you couldn't ever understand it. But in 9th grade, this is all we need to worry about. If you're really curious, take some more science courses, take some physics courses, go to college and study this stuff and have that be your major. There are people's majors that are just studying electromagnetic spectrum because it's that complicated. But for right now, this is all we need. So, Mr. Martineau, saying hi from Miss Mangiarelli, here from the House of M. Toons has left the building. Have a wonderful day. We'll talk to you soon. Thanks. Bye.